Hello and welcome to G Fun Facts Online, where we dive into the most fascinating corners of science and the cosmos. Today, we're tackling one of the biggest questions ever asked. Are we alone in the universe? The answer might not come from a spaceship landing on Earth, but from something far more subtle, a quiet symphony playing out across the galaxy. We're going to explore how the gentle rumbles of distant stars, literal starquakes, are becoming our most powerful guide in the hunt for alien worlds and extraterrestrial life. This is the science of astroseismology, and it's changing everything we thought we knew about finding a second Earth. So what exactly is astroseismology? The name sounds complex, but the idea is beautifully simple. Just like geologists on Earth study earthquakes to map out our planet's core, mantle, and crust, astronomers study the vibrations of stars to understand what's happening deep beneath their fiery surfaces. These vibrations are essentially sound waves bouncing around inside the star. They're not loud booms you could hear with a space microphone, of course. Instead, these oscillations cause tiny, almost imperceptible changes in a star's brightness. A star might get a fraction of a percent brighter, then dimmer, in a regular, repeating pattern. By pointing incredibly sensitive space telescopes at a star for a long time, scientists can record these minute flickers of light. They then use mathematics to break down this pattern into its individual frequencies, much like a prism splits white light into a rainbow of colors. Each frequency, each note in this stellar symphony, corresponds to a different kind of wave traveling through the star's interior, carrying with it a treasure trove of information. There are two main types of these stellar sound waves that astronomers listen for. The first are called pressure modes, or P modes. These are high-frequency waves, very much like the sound waves we're familiar with. They are driven by pressure fluctuations and are most prominent in a star's outer layers. They give us a great picture of what's happening near the surface. But the real magic comes from the second type, gravity modes, or G modes. These are much lower frequency waves. Instead of pressure, their restoring force is buoyancy, similar to how a cork bobs up and down in water. These G modes are trapped deep within the star's radiative core. This is incredible because it means they give us a direct window into the very heart of a star, a place that is otherwise completely hidden from view. By carefully analyzing the complex interplay between all these different P modes and G modes, astronomers can build an astonishingly detailed model of a star. They can figure out its internal structure, its chemical composition, and even its age. And knowing the star in such intimate detail is the absolute key to understanding the planets that orbit it. You might be wondering, okay, knowing about the star is cool, but how does that help us find life? This is where astroseismology becomes a revolutionary tool for exoplanet hunters. We've already discovered thousands of planets outside our solar system, but a simple discovery isn't enough. To know if a planet could harbor life, we need to characterize it, to know its size, its composition, and its age. And all of that starts with knowing its parent star with extreme precision. Let's start with a planet's size. One of the most common ways we find exoplanets is the transit method. This is when a planet passes directly in front of its star from our point of view, causing a tiny temporary dip in the star's brightness. The amount of that dip tells us the size of the planet relative to its star. So, if you have a big star, the same dip in light could be caused by a much larger planet. Before astroseismology, our estimates of star sizes could be off by 20, 30, even 50%. This meant our estimates for planet sizes were just as uncertain. But by listening to a star's symphony, astronomers can now calculate its radius with an accuracy of just a few percent. This is a game changer. It allows us to determine the planet's true size with confidence, letting us know if we've found a small, rocky world like Earth, or a giant gas planet like Jupiter, which is far less likely to be habitable. Next up is composition. Are we looking at a rock or a big ball of gas? To figure this out, we need a planet's density. We get the planet's size from the transit method, as we just discussed. We can get its mass using another technique called the radial velocity method, which measures the slight wobble of the star caused by the planet's gravitational tug. Mass divided by volume gives you density. But here again, the calculation of the planet's mass from that wobble depends directly on knowing the mass of the star itself. Astro-Seismology provides the most precise measurements of a star's mass available today. By nailing down the star's mass, we nail down the planet's mass, which means we get a highly accurate density. A high density points to a rocky world, a potential home for life. A low density tells us it's a gas giant. One of the most profound contributions of astroseismology is its ability to tell time. Cosmically speaking, it gives us the most accurate age for a star we can possibly get. And since we believe planets form at roughly the same time as their host star, knowing the star's age tells us the age of the entire planetary system. Why is this so critical in the search for life? Well, on our own planet, it took billions of years for life to evolve from simple microbes into complex organisms. If we find a rocky, Earth-sized planet in the right place, but its star is only a few 100 million years old, complex life probably hasn't had enough time to get started. But if astro-seismology tells us that system is 4, 5, or 6 billion years old, that's a much more compelling target. It means the planet has had a long, stable history, providing a potential crucible for life to emerge and flourish. Astro-seismology can even tell us about the architecture of a planetary system. By studying how a star's rotation affects its vibration frequencies, astronomers can figure out the tilt of the star's spin axis. They can then compare this to the orbital plane of its planets. Is the system neat and tidy like our own solar system, with all the planets orbiting in line with the Sun's equator? Or is it a chaotic mess, with tilted orbits suggesting a violent past? This provides crucial clues about how that system formed and evolved over billions of years. This brings us to the famous habitable zone, often called the Goldilocks zone. This is the region around a star where the temperature is just right for liquid water to exist on a planet's surface. Not too hot, not too cold. But this zone isn't a fixed location in space. As a star ages, it gets brighter and hotter, and its habitable zone slowly moves outwards. A planet that was once in a perfect spot might later become a scorched desert. Astro-seismology helps us map this moving target with incredible precision. By giving us the star's exact mass and luminosity, it defines the boundaries of the habitable zone right now. And by telling us the star's age, it lets us reconstruct the history of that habitable zone. We can ask, has that Earth-like planet been sitting comfortably within the habitable zone for the last 4 billion years? That's a much better candidate for life than a planet that only just entered the zone recently. Furthermore, the chemical makeup of the star, which can be cross-referenced with astroseismic data, is another vital clue. Stars with higher metallicity, that's an astronomer's term for any element heavier than hydrogen and helium, are more likely to have formed rocky planets in the first place. Those heavy elements are the very building blocks of planets and of life itself. While astro-seismology has us listening to distant suns, the broader field of seismology is also being used to hunt for signs of life much closer to home. Let's talk about Mars. Since 2018, NASA's InSight lander has been sitting on the Martian surface, using a sensitive seismometer to listen for Marsquakes. The data has been nothing short of spectacular. It has given us our first detailed map of the Martian interior, revealing a surprisingly large and completely liquid core. But even more tantalizing are recent analyses suggesting that seismic waves are behaving in a way that could indicate the presence of liquid water deep beneath the surface. These underground pockets, shielded from the deadly radiation that bombards the Martian surface, could be potential havens for microbial life. Some research even suggests that the friction from the grinding of rock during a Marsquake could produce hydrogen gas, which subterranean microbes could potentially use as a food source. So the very shaking of the planet could be feeding hidden life. Even our own moon has a story to tell through its quakes. The Apollo missions left seismometers on the lunar surface that recorded thousands of moonquakes between 1969 and 1977. Scientists are still analyzing that old data with modern computers and techniques. While nobody expects to find life on the moon, these moonquakes tell us about its internal structure and its violent history of being pummeled by meteoroids. This helps us better understand the chaotic conditions of the early solar system, when both the moon and the young Earth were being shaped. We are truly living in a golden age of discovery, and the future of stellar seismology looks brighter than ever. We have a new generation of powerful space telescopes that are feeding us an unprecedented amount of data. NASA's TESS mission, the Transiting Exoplanet Survey Satellite, is currently scanning the entire sky, looking for planets around the nearest and brightest stars. But TESS is also a phenomenal machine for astro-seismology. It's providing high-quality seismic data for a huge number of stars that we already know have planets, dramatically increasing the number of well-characterized worlds in our catalogs. And coming soon, scheduled for launch in 2026, is the European Space Agency's Plato mission. Plato stands for Planetary Transits and Oscillations of Stars, and its name tells you everything. This mission is specifically designed to find and study Earth-like planets orbiting in the habitable zones of Sun-like stars. Astro-Seismology is the absolute cornerstone of this mission. Plato will deliver exquisitely precise measurements of the mass, radius, and age for every star it finds a planet around. This will give us the most detailed picture yet of these other Earths and their potential to host life. This fire hose of data will also help us build more sophisticated tools for sorting through our discoveries. Scientists are already developing things like the Earth Similarity Index and the Planetary Habitability Index. These are attempts to rank exoplanets based on their life-hosting potential. The precise data from Astro-Seismology will be the fuel that powers these indices, creating a reliable roadmap for future telescopes, like the James Webb Space Telescope, to follow up on the most promising targets. The search for life beyond Earth is one of humanity's most profound undertakings. While we haven't found that definitive signal yet, the science of astro-seismology has handed us an incredible new sense. We are no longer just looking at the stars, we are listening to them. We're learning to hear the music of their vibrations, decoding the secrets of their cores, and through them, gaining a breathtaking understanding of the alien worlds that circle them. We are learning to filter the cosmic noise and focus our search on the planets with the best chance of being a cradle for life. The symphony of the stars is playing all around us, a constant reminder that the universe is a vibrant, dynamic, and mysterious place. And if we keep listening carefully, one day, we might just hear the faint but unmistakable harmony of life on another world. Thanks for tuning in to G Fun Facts Online.